Look around you. Everything you see, from the largest stars to the smallest grains of sand, is influenced by a fundamental force: gravity. Gravity is the force of attraction between any two objects that have mass. This means that everything in the universe pulls on everything else, no matter how small or how far apart. The more massive an object, the stronger its gravitational pull. That's why we feel Earth's gravity much more than the pull of a book on a table. We don't feel the pull of objects around us because the Earth's gravity is much stronger. Gravity keeps us grounded on Earth. It's why objects fall to the ground when we drop them. But gravity's influence extends far beyond our planet. It's what holds the moon in orbit around Earth, keeps the planets in orbit around the sun, and even governs the motion of entire galaxies. Gravity is the invisible force that shapes the universe. In the 17th century, Sir Isaac Newton formulated the law of universal gravitation, a mathematical description of this fundamental force. Newton's law states that every object in the universe attracts every other object with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This means that the more massive the objects, the stronger the gravitational attraction between them. And the farther apart they are, the weaker the gravitational force becomes. Newton's law is represented by the equation F equals G times the product of m1 and m2 divided by r squared. In this equation, F is the force of gravity, G is the gravitational constant, m1 and m2 are the masses of the two objects, and r is the distance between their centers. Newton's law of universal gravitation revolutionized our understanding of the universe. It provided a simple, elegant explanation for why planets orbit stars, why tides rise and fall, and countless other phenomena. Let's say you want to calculate the gravitational force between two bowling balls, each with a mass of 5 kilograms, placed 1 meter apart. The gravitational constant, G, is approximately 6.674 times 10 to the power of negative 11 Newton meters squared per kilogram squared. Plugging these values into Newton's equation, we get F equals 6.674 times 10 to the power of negative 11 Newton meters squared per kilogram. Squared times the product of 5 kilograms and 5 kilograms divided by 1 meter squared. This simplifies to F being approximately 1.67 times 10 to the power of negative 9 newtons. This force is incredibly small, far too weak to be perceptible. It highlights the fact that gravity is a relatively weak force, especially over short distances and between objects with relatively small masses. However, when dealing with massive objects like planets and stars, the force of gravity becomes incredibly powerful. It is this immense gravitational force that governs the motion of celestial objects, keeping planets in orbit and stars bound together in galaxies. The effects of gravity are all around us. The most obvious example is the force that holds us to the Earth's surface. But gravity is also responsible for a wide range of other phenomena. Ocean tides. The gravitational pull of the moon and the sun causes the oceans to bulge, creating high tides. As the Earth rotates, different parts of the planet experience these bulges, resulting in the regular cycle of high and low tides. Planetary orbits. The planets in our solar system are held in orbit around the sun by its immense gravitational pull. The sun's gravity acts like an invisible tether, keeping the planets from flying off into space. Galactic structure. Gravity is responsible for the formation and structure of galaxies. The Milky Way, our home galaxy, is a vast collection of stars, gas, and dust, held together by the combined gravitational pull of all its constituents. These are just a few examples of the pervasive influence of gravity in our universe. From the smallest particles to the largest cosmic structures, gravity plays a fundamental role in shaping the universe we observe.